In this video, we're going to look at an application of exponentials and logarithms modeled on a typical life sciences scenario where we're looking at a compound, a drug, which is being metabolized over time, and the metabolism is given at some rate. Here we're given the initial amount of caffeine in the body, calling it A of t, and what we know is that at time 0 in hours, we have 100 milligrams. We can add units to our chart here. And what we're told is that once we have our cup of coffee and that caffeine is in our system, then we're going to lose the caffeine. It's going to be metabolized and excreted at a rate of 17% per hour. The word continuous here is going to play a role. We'll see that a bit more in a second. But the idea basically is that after 1 hour, we've gone down by around 17%. So this is 100 milligrams and 80 milligrams and 60. If we've lost 17%, we'll be down a little bit above 80. But then we lose 17% of what's here in the next hour. That's not going to be as big. And then we lose another 17% of what's there. Well, if we see how the shape of that curve starts developing, we start seeing what looks like an exponential decay curve. And that's in fact what the mathematics is going to reinforce. We were told the loss rate was 17% per hour. And one way we could achieve that is to say, if the statement said we were losing exactly 17% per hour, then the model we get is going to be of this form here, 1 minus the rate, 0.17 to the power t. There are 100 milligrams to start, and so our A of t would be 100 times this value here, which we can even translate into something a little more precise, 0.83 to the power t. What does this model predict? It predicts that exactly at t equals 1, we are going to have exactly 100 times 0.83 times to the power 1, which is 83 milligrams, or exactly a 17% drop. Another alternative, which is actually more used in sciences, and we'll explain why in a bit, and it's what would apply in this scenario here because that phrase continuous rate was used, and it turns out that it has a special meaning. That continuous rate of 17% per hour has the same building blocks. We have our amount, A of t, is going to be our base amount, 100, but instead of the 17 being 100% minus 17%, 1 minus 0.17, we get an exponential. It's a decay, so it's negative, and we put the 0.17 inside as a multiplier up here. Now that might feel totally different at first glance. I'm going to show you that in fact it's quite similar. In particular, we can compare the values. At t equals 1, A of 1 is going to equal 84.36 milligrams. Now these two numbers are very, very similar. We're only off by 1 milligram out of 100 at this point here. There's also another way to rephrase this, which makes the contrast or similarities even more stark. At the end of the day, if we have a product in our exponent, one of the rules of manipulating exponents is that we can nest them. We can talk about e to the negative 0.17 all to the power of t. And it turns out that that value, just calculating the inside part, is exactly 0.8436 and so on. So actually approximately that to the t. So this expression where we lose exactly 17% per hour, we see that loss of 17% in this form here. When we say the continuous rate, we get a slightly different scaling value, but it's very, very similar. Why do we have the two models? Well, this 17% per hour is going to come up when we talk about derivatives. What we're saying here is that at any point, the derivative is going to be exactly, or the slope is going to be exactly decaying at 17% of the amount. And that's a little different from saying after 1 hour, I know exactly how much I've lost. Let's take the forecast from these two models out a bit further, out to 10 hours, and see what we get. If we do that, we're going to have 100 times 0.83 to the power 10 on this side here, and that's going to be approximately 15.5 milligrams of caffeine left over. If we use the model on this side and forecast 10 hours into the future, we're going to have our 10 is our t in the exponent. And when we calculate that out, we get approximately 18.3 milligrams. This would be one of those scenarios where we say that these are similar. They've both lost about 80%, 80 to 85% of their caffeine, but they're certainly not equal. In the next video, we're going to dive into the issues around continuous rate versus other rates and how they get phrased and how you know which of these two models to go directly to if you're given that kind of quantity, like 17% loss per hour. How do you know which of these two to use? It is quite clear-cut in most cases, but I just want to remind you that these two models do exist, and you should be comfortable with both of them.